the practical work and also the slides are available on this link. So it's the GitLab repository of the remote sensing group of Professor Florence Tupin. So on this link, you will find indeed the notebook, the Python notebook that we are going to use, the Jupyter notebook. And also there's a link that points to the slides that we have seen in the theoretical session. So if you click on the notebook, then you are able to download it and then to open it in Google Colab or to run it locally if you want. But there are some functions that well, are compatible with the Google Colab. So if you run it locally, I'm not sure that it will work straightforwardly. It might need some adaptation. So by using Google Colab, I'm sure that everybody has the same platform and you won't have any bug in the code. But then, I mean, you can run it locally at home if you want. So I'll just describe what you're going to see in this hands-on session. So it is, so the code has some gaps that we're going to fill together. So I'm gonna anyways provide the solutions. We will like create some tools that then you can reuse and play with it if you want to visualize and process some SAR data. So first of all, we will start with, well, simply downloading and reading a SAR image. And we will have a look at how to visualize the phase and the amplitude information of a synthetic aperture image. In this practical work, we will only work with single channel, single look complex SAR images. So we're not gonna see any interferometric image or polarimetric image. It's simply a single channel SAR image in single look complex format. We are going to implement a simple visualization tool, but it will already makes you understand the difference between natural images and optical images, and you will start to see that you need some adaptation when you want to work with SAR images. And then we are going to analyze the distribution, the empirical distribution of SAR images, and we will see how well the theoretical model that was proposed by Gutmann fits with the real images. Okay, then what we are going to see is some speckle reduction techniques. So we will implement some simple techniques, what was called the pixel-based speckle suppression techniques. And then we will use the last algorithm that was presented by Florence Tupin in the theoretical session, which is the Merlin algorithm, which is the self-supervised algorithm that relies on the decomposition of the SAR image between a real part and imaginary part. We have released a Python package of the trained network. So we're going to install it and then use it to suppress speckle from a SAR image. We are gonna work with images from different sensors. We are not going to download the images from the, like for instance, from the ESA website or from the DLR website. I already have downloaded some images, but well, I think that you all know that Copernicus data are freely available. There are different ways to download this data, and then there are also some TerraSAR X data that are acquired by the well, by the German sensor TerraSAR X, and images are provided by the DLR, which is the German space agency, basically. And there are some data that are also freely available on the Airbus website. So you can also well, freely download and analyze some SAR images acquired by TerraSAR X. Okay, so I have already run the first two cells of this notebook that just, well, download some data that we are going to use and, well, mostly some libraries that we will need, some simple functions and, well, import the libraries that are needed to run the code. Okay, so we can start by visualizing a SAR image. I'm going to recall some of the concepts that have already been covered during the theoretical part, but during the hands-on, recalling these concepts, it will maybe, well, print on your memory what has been said before. So let's start by reading a SAR image. So that's a TerraSAR X image that you have already seen before, which covers the Tour Eiffel part of the city of Paris. It's a single loop complex image, okay? So in each pixel, you have a complex value. When you download the images from the different websites, there are different conventions depending on how the data are stored. So sometimes you can have, indeed, in each pixel, a complex value. Sometimes you have an image which has two channels, one for the real part, the other one for the imaginary part. So the message is, have a look at the README or at the metadata to see how the data are stored so that you can know what you are manipulating. So in this case, in each pixel, you have a complex value. So the image is a bidimensional array where in each pixel you have a complex value, which encodes the real part and the imaginary part of a SAR image. So first of all, we can visualize the phase information of a single loop complex SAR image. To visualize the phase, given that data are in complex format, you can use the function provided by the NumPy library, for those who are not familiar. So it just numpy.angle, and then in input, we will just give the image array. And then the numpy.angle provides values which are between -pi and pi, okay? So in this sense, the phase is wrapped, meaning that, well, values are wrapped between -pi and pi. So when you visualize it with the matplotlib library, you have to select the minimum and the maximum value. So you will just display values between -pi and pi. Of course, whenever you have questions, do not hesitate to interrupt me and ask your questions. So if we visualize the phase, you don't actually have much information if you only have a single SAR image. So, well, the phase is uniformly distributed between -pi and pi. So if you have a single SAR image, you won't retrieve any information from the phase information. It's only if you have several SAR images that the phase information will be useful to do interferometry. So it's not the single phase information which is informative, it's the difference of phase between images that will provide information about elevation and topography and geometry of the scene. If you have a single SAR image, you often discard the phase and you only keep the amplitude or the intensity information, which is the square of the amplitude. So you're only looking at the modulus of the complex SAR image.
So as I understood, what's actually encoded in the image is just the modulus of the amplitude, no?
What's encoded in the image is the modulus of the amplitude and the phase information. What we are displaying here, it's only the phase information. Then we're going to look at the amplitude as well. So the amplitude is just the magnitude of a SAR image. So in order to visualize it, we take the absolute value. So if you visualize the SAR image in the naive way, you will see what happens. It should be faster than, than that, but it will come. Okay. What do you see here? Do you have any clue why we see this dark image if you visualize the image in this way? Yes. Wait for the microphone, maybe. Sorry, that's going to be a tennis match.
Yes, maybe data is not normalized.
So what the matplotlib function is doing is that it is taking the minimum and the maximum,
Yeah.
it shrinks it between 0 and 255,
Yeah, but I think
and it
that
visualizes this information. So it is normalized automatically.
yes,
between
but the
0.
spectrum is compressed, so you see the values that are not displayed in the correct way. You have like to equalize the histogram to see correctly, right?
So, yeah, indeed. First of all, let us have a look at the histogram of the amplitude. So I'm not even displaying the full histogram because the maximum of the image is, so the range is between 0 and 42,000, and I'm only displaying the histogram between 0 and 5,000. So what you see is that the majority of the values are between 0 and 1,000. However, when we plot the image the naive way, we are displaying everything that is between 0 and the maximum of the image, which is 42,000. So everything becomes compressed, basically. So we don't, we cannot see the contrast that our eyes would like to look at. So for visualization purposes, what we do is that we apply a thresholding. I'll do this. So we apply a thresholding so that we can see this part of the information which is interesting for visualization purposes. But bear in mind that when you process our image, you always process the whole information. You don't want to discard information when you do processing. You discard information only for visualization purposes. So let us implement this function. The convention that is used to visualize our image is to apply a threshold, and the threshold is based on the statistics of the SAR image that you want to visualize. So you often visualize the data that are ranging between 0 and then the mean plus 3 times the standard deviation of the SAR image, of the amplitude, of course, of the SAR image. So we're going to do that. It's going to be really simple. So here, what I'm doing is that I have defined my threshold, which is based on the statistic of the image, and then I tell to my matplotlib library to visualize data that are comprised between 0, where it's not specified, but it's 0, and then I set my maximum value to threshold. What we see is something which is quite different to what we could see before. So that's the image that we were looking at without any thresholding. And now, by simply thresholding, well, we can see much better the content of the image, and we can well, visualize the urban environment. We can see the river, which is in black. So why the river is in black? It's because it does not convey any power towards the radar, because of the, well, when you send a pulse with an incidence, with a given incidence angle, and you have a flat surface, then you have the Snell-Descartes law that tells you that the electromagnetic wave will be bounced in the direction which is opposite with respect to the sensor direction. So no component is coming back to the sensor. Instead, the urban environment is reflecting a huge component towards the sensor. So buildings appear in white, meaning that they convey a huge power, so a huge amplitude towards the radar. So I'm gonna ask you one question, but I think you already know the answer because it was given before. So in this case, the sensor is flying, well, even from the top to the bottom or from the bottom to the top. But the question is the sensor on the right-hand side of the image or is the sensor on the left-hand side of the image? And why?
Yes, so this distortion are directed towards from the right to the left, which means that the highest place, like the closest object to the sensor, are the closest are the one that's showing first.
Yes, perfect, exactly. So that's the reason why we can say that the satellite is on the left of the image. So maybe one takeaway, it's something that was mentioned yesterday also by Michael. When you do deep learning, sometimes you apply some data augmentation techniques in order to, well, augment your data set. But there are some techniques that are not adapted to any sort of data. So by convention, when you download SAR images, well, image providers give you images where the sensor is always on the left. So if you flip this image with respect to the vertical axis, well, you are changing completely the geometry of the SAR image. So I wouldn't advise you to apply some flipping to augment your data if you are interested in capturing the geometric information of the SAR image, because you're not going to augment your data. You're just, well, increasing the complexity and inducing some invariances that in fact are not true, because then for practical applications, you will always see images where the sensor is on the left. So you don't want your network to learn something that is not true in the real world. Okay, so I'm going to, well, we're going here to re-implement the same function that we defined before, but okay, so we are giving an input amplitude data. So I'm gonna suppress this, okay. It just, well, in this way you will have a title to your image, and you can change the size of the figure, and you can decide whether you want to apply thresholding or not. So if you set the threshold to 0, it means that you don't have any threshold, so you display the image between 0 and the maximum value. Otherwise, if you don't say anything, by default, we are applying a truncation between 0 and the mean plus 3 times the standard deviation. So again, we will see the black image and the image after the thresholding. And here you see the statistics of the image. So you can see the mean value and the standard deviation that are computed on the amplitude image. Okay, now we can move to analyze the distributions of a single look SAR image. We are gonna work with another image which is acquired by the Sentinel-1 sensor operated by the European Space Agency. It's an image that comprises well, some agricultural and rural area and also some water area in the Netherlands. You can have a look at an optical image in case you want to compare to an optical image, and we are going to select an homogeneous region where we are going to analyze the statistics, the empirical distribution of the SAR image, and we will see if the empirical distribution fits with the theoretical distribution that is provided by Goodman. So here is the image. So it is quite big. So it's like 1,024 by 3,000 and something. But we're just going to focus on a homogeneous area. Why on a homogeneous area? Because, well, if you want to analyze the statistic and you take an heterogeneous area, you are mixing distributions that are coming from different physical objects. Okay, so you have to model it. So you cannot expect that a model that has been built for a physically homogeneous area will hold if you select a big window with many edges and fields having different reflectivities. So I am recalling here that we are dealing with a single look complex SAR image. So we have a complex value in each pixel. This complex value can be expressed either as the complex sum of the real part and the imaginary part, or as the product of the amplitude for the exponential of g and the phase information. So we're going to analyze the distribution of all these components where the amplitude is the magnitude of z, but it is also the square root of the sum of the squared real part and the squared imaginary part. And the phase, which is the arctan of the imaginary part divided by the real part. And finally, you have the intensity. Why do we look at the intensity? Because it is proportional to the power of the signal. The intensity is the squared of the amplitude. And I am recalling here that the intensity is defined by Goodman as the product between the speckle and the reflectivity, where the reflectivity is the information that is coming from the scene. And the speckle is given by the fact that within a resolution cell, you have many scatterers that you cannot distinguish because they all fall within the same resolution cell. And it is because of the coherent summation of these elementary contributions that you have differences in phase, and this creates a random walk in the complex plane. So even in a homogeneous area, between two pixels that are one on the side of the other one, you can have completely different amplitudes because of the difference of phase and the difference of arrangements of the elementary scatterers within the resolution cell. So I have selected here an homogeneous area on the water part of the image, but if you want to select a different area, for instance, on an agricultural field, feel free to select some different area, provided that the area is big enough so that you can fit some distribution. Well, do not select an area of 4 by 4 pixels, otherwise you can not look at the histogram. So what we're going to do here is to fit the different distributions that I have provided you on the different components that characterize a SAR image. So let us do that. So I'm going to complete the code so that we can have a look at it together and have a look at the histogram and the theoretical distributions. Yes?
Can you just zoom in a little bit?
What?
So that we can read. Can you just zoom in?
Ah, yes. Sorry.
Yeah, thank you.
Is it fine? Yeah, sorry, you're right. Okay. So we will work with this crop, and we're going to select the different quantities and then plot the different distributions. Okay, so there are pre-implemented functions to extract all the different quantities. So here I'm plotting the homogeneous area that I have selected, which is homogeneous, but there's the speckle, so it doesn't look homogeneous, but it is. So I'll just leave here so that you can have a look at it, but if you are even faster than me and you already have plotted the distribution, that's fine. I'm gonna jump to this point in a few seconds. So I have defined things this way, but if you want to take the intensity, you can also take the squared of the real part plus the squared of the imaginary part. I mean, there are many different ways to compute these quantities. I'll try to go to the next step, hoping that you have all copied this part, but I can come back to it if it's necessary. So here you have an example on how to fit a theoretical distribution on an empirical histogram, and it is done for the real part, whose distribution is Gaussian. So we're going to do the same for all the other quantities, and we will use the appropriate distribution at each time. So the imaginary part follows as well a Gaussian distribution, so I'm going to copy to mimic what is done for the real part. And the distribution is normal, so I will select the normal distribution. Then I'll move to the phase. So it's a uniform distribution, so we're not, well, we could fit a horizontal line, but I haven't done it here. And then here we will look at the, at the intensity. So it was defined as this one. And its distribution is exponential, so I'm gonna use this pre-implemented function that you have here. So I'm gonna fit an exponential distribution on the intensity, and finally, I'm gonna fit, what is called a Nakagami distribution on the amplitude information. So we're just going to have a quick look at the histograms, and then I'll come back to the code so that you can see how it is done in case if needed. So here we have the histogram of the real part, and we see that the Gaussian distribution fits pretty well. The real part, the same for the imaginary part. Then we have the phase, and we can see that it is pretty uniformly distributed. And finally, we have the intensity, and we see that it follows an exponential distribution as expected. And finally, we have our amplitude, which follows the Nakagami distribution. We see that there's a good superposition between the orange theoretical line and the blue empirical histogram, which means that which means that the distributions that are provided by Goodman, they fit pretty well with the data. So if you want to work with SAR images, please remember that you have the distributions that are describing all the quantities that you want to look at, even interferometric data or polarimetric data. So look for them on the website. You will find all the distributions, so use them, and well, be careful. You're not dealing with natural images, so take it into account. So maybe we can start to move ahead, and so we will start to see how we can characterize the homogeneity of the scene on a SAR image. So, well, as it has been said before, the intensity is given by the product between the reflectivity and the speckle component. So, because you have a product, the stronger the reflectivity, the higher the variance of a SAR image. So in standard computer vision approaches, when you deal with natural images and you want to detect the homogeneity of the scene and look at edges, for instance, you can take the standard deviation. But in this case, you cannot do it because the standard deviation is linked to the reflectivity of the scene. It's not the same on the whole image. So you have to normalize your standard deviation by the mean if you want to look at the homogeneity of the scene. And well, this simple indicator is called the coefficient of variation. It's really simple to compute. We're going to compute it locally on the whole image by using a moving average window. So here I'm going to define my moving average window. I have defined the size of the window as 7, but you can play with it and try to make it bigger or smaller, and you will see how it affects the output image. So here I'm just defining an array where, so the shape of this matrix is 7 by 7, and in each value I have 1 divided by 49. Okay, so it's an average filter. It's a mean filter, and then I'm going first to compute the mean image. So I'm going to average pixel in intensity. So this operation is called the multi-looking. Please be careful that when you average incoherently pixels, you have to do it in intensity. Why you have to do it in intensity? Because the average of intensity values corresponds to the maximum likelihood estimation of the reflectivity. If you average pixel in amplitude or in the log domain, you will have a biased estimation of the reflectivity, meaning that you will have a correction to apply. You are not estimating your reflectivity if you average pixel which are not in intensity. So that's why the processing here is done in intensity. So I'm just convolving my intensity image with the filter that I have defined. Then I'm going to compute the variance, okay, which is well, the subtraction between the mean of the squared intensity minus the mean of the intensity to the power of 2. And finally, I can compute my coefficient of variation, which is just the ratio between the standard deviation and the mean. So I have just added a small value in case I had some zeros in my mean, because I don't want to divide by 0. So here I have taken the ratio between the standard deviation, so the square of the square root of the variance, and and the mean. And then I am displaying the coefficient of variation, and I'm also displaying the variance. So I have taken the square root because otherwise you will see everything black because the variance has a high dynamic range. Yes. Yes, I'll try to do that. Okay, you can have a look at it. So I'll just quickly display the results and then I'll come back to the code so that you can have a look at it. But in the meantime, so here you have the image. Here you have the coefficient of variation, and you see well, edges stand out, while all homogeneous areas have the same coefficient of variation. While if you display the variance, you will see that the variance is directly linked to the reflectivity information. So you cannot use it as an indicator of homogeneity of the scene. So I'll just come back to here so that you can copy it, and then we will move to the next part, which consists in implementing two simple speckle filtering algorithms and then compare it with most advanced self-supervised deep learning ones. Yes.
In the last result is 3 images. I got it.
What?
I got 3 images in the
Yes.
last code. And did you use de-speckling in which step?
Here you mean?
Yeah, in the last one. I have 3 images, yeah?
Here?
Yes.
1, 2, and 3.
3, yes.
Yeah.
One of them is de-speckled or not?
I haven't done any despeckling here.
Okay. It's just
I haven't done any despeckling.
all of them are intensity.
Yes.
Okay.
So here it's the original image, okay? And here is the coefficient of variation. And here I'm showing, well, in fact, I have taken the square root of the standard deviation just to show you that it is directly linked to the reflectivity, okay? It looks like the original image, in fact, the square root of the standard deviation.
I mean, this is R because you said I is equal to reflectivity multiplied by speckles, yes? R. Yeah, this is R, the last one.
I mean, the last one is the square root of the standard deviation, but because of the fact that the model is multiplicative, basically it comes back to looking at the amplitude, yes. Because L is equal to 1 in this case, because we are working with single look image, and L is the same in the whole image, yes.
Okay.
Is it good for everyone? Can I move to the next step? Okay, I'll try to go ahead. So here we're going to work with even another image. So this image is acquired by the TerraSAR X sensor in strip map mode. And it's taken over the area of Sendai in Japan. And it's a small image. Its size is 512 by 512 pixels, but it helps us to analyze the behavior of the different filters that we are going to implement. So in this case, the convention is not the same as before. In the image that you have downloaded, the image is composed by 2 channels, where the first channel is the real part and the second one is the imaginary part. So you just need to know it when you download the image so that you can properly produce the intensity and the amplitude. So I have created the intensity, which is the sum of the squared real part plus the squared imaginary part, okay? And then I am visualizing the amplitude information, which is just the squared root of the intensity. So here you can see the image that we are going to deal with. What is interesting in this image, and the reason why I have chosen, is that there are some homogeneous areas. So when we do the speckling, we want to suppress speckle from homogeneous areas, but at the same time, we want to preserve edges. And in this image, we have both classes. So we have homogeneous areas. We don't want to introduce artifacts in homogeneous areas. And at the same time, we want to be careful when suppressing speckle, because we don't want to destroy too much information. We want to preserve the information that is contained in the image. So we want to be precise near the edges. And that's quite challenging, as you will see. So the first, the simplest way actually to suppress speckle from SAR images is to average samples incoherently in intensity, okay? What happens? Well, depending on the size of the window, you are going indeed to filter out the speckle in homogeneous areas, but you're going to reduce the resolution of the image depending on the size of the window that you have chosen to do the averaging. So I'm using the local window that we have defined before, whose size was 7 by 7. And I am applying this window to the image. And this is what you get. Is it satisfactory, this result? How does it seem to you? Well, maybe for homogeneous areas, it's quite okay. We have, well, maybe improved the estimation on this area, but do we have a good preservation of edges or the urban area? Not really. So maybe we can try to improve it. One way to improve this simple filter is to take into account the coefficient of variation that we have computed before, which is an indicator of the homogeneity of the scene. This is the Lee filter, which is, well, quite famous. It's one of the first filters that was proposed to suppress speckle from SAR images. And the idea, as you see here, is that, well, you have the multi-looked image, so the image after the filtering with the moving average filter, and you have the intensity image. And you want to take the best of the two worlds, meaning that it's okay to average pixels in homogeneous areas because it filters out the speckle, but you don't want to destroy information near the edges. So if the coefficient of variation tells you that the area is homogeneous, then we are going to stick with the mean. If instead the area is heterogeneous, then you're going to give back the intensity information. So first of all, here I'm going to compute again the coefficient of variation on this new image. So that's exactly the same way as it was done before. And we can have a look at it. So again, so here I'm displaying the square root of the variance. So you see, it's not indicating the homogeneity of the scene, while the coefficient of variation is a better indicator. So it is low if the area is homogeneous, okay? It is high if the area is heterogeneous. So it highlights edges somehow. So we can use it to weight the balance between the intensity image and the average image. So that's what we are going to do here. So we are going to define K. So I gave you the formula here. k is going to be 1 minus 1, because we are dealing with a single look complex SAR image, divided by the empirical coefficient of variation. Okay, and then we have that the filtered image is going to be the average image, so the multi-looked image, plus k intensity minus the mean. Intensity minus the multi-looked image. And this is what we get. So that's the image that is filtered by the Lee filter. So it's an improvement with respect to the average image. So that's the average image. So the resolution is really poor. With the Lee filter, we have an improvement. The result is the same as the multi-looking filter in homogeneous areas, but we have better preserved the intensity, I mean the edges, but there's some speckle that is left, of course. So it's better, but still we can achieve better results with more sophisticated algorithms. And that's what we're going to do. So here we're going to apply the neural network that was trained with the strategy that was presented before by Professor Florence Tupin. So I'm going to briefly recall the rationale behind the framework that is developed. So this network was trained in a self-supervised manner on single-look complex SAR images. And the basic idea is that if you have two images that are representing the same scene, but the noise component is independent between the two images, you can feed your neural network with one image, and you can ask to minimize the distance between the output and the second image. Because the noise is independent, the task is impossible. So the network cannot create another noisy image starting from the first noisy image. So the network cannot mimic the random component. What the network can do, at best, is to produce the common information, so the deterministic information. What these two images have in common is the underlying scene, which is the reflectivity. So the network is trained to produce a noisy image from another one, but because this task is impossible, it will produce the underlying scene. So basically, it will implicitly learn to suppress the speckle component from the noisy image. So with this strategy, if you have a single SAR image, you can train a neural network to suppress speckle from SAR images. So that strategy is not specific to any network structure, nor it is specific to some sensor. So you can actually apply to any sensor, and you can also use any network architecture within this framework to train a neural network for speckle reduction. So we have trained our model with TerraSAR X images in strip map mode, and we also have done it for TerraSAR X images in spotlight mode. We have one model for each modality because the resolution is not the same, maybe the spatial correlation is not the same. So you have to, well, my advice is that you train a neural network for your given image modality and resolution, and it is better to use a neural network that is specific to the image that you want to process. So if you are dealing with TeraSAR X images, do not use a neural network that is trained for speckle reduction on Sentinel-1 images, because I'm not sure it's gonna give you the result that you want, because there's going to be a domain gap between the two images. So there's a domain shift between the data that you are using. So please, if you are dealing with data that are coming from one sensor, use speckle reduction networks that are trained for that sensor, okay? So the approach here that we have developed, well, we call it Merlin because it had something magical, which is the fact that we are exploiting the phase information, which is not informative, as you have seen at the beginning of the practical work, but we have used it to decompose the complex SAR image into real part and imaginary part. We have released the Python package for that we are going to, how to say, we're going to add also other approaches that we have developed and that are going to be developed. So we're going to install it and then to apply it on our image. So the installation is pretty fast. Then I just created the folder where to store the image. And here I am with, well, 3 lines of code making my neural network run on the image and producing the result. So the neural network is running on the GPU, and soon enough we will be able to see the result. Please bear in mind that the results are stored in amplitude, okay? So the speckling is over. The results are stored in this folder. So you can have a look at the noisy image, at the imaginary part, at the real part, and then you can have a look at the intermediate estimation that is provided from the real part, which is denoised. So here for the imaginary part, here for the real part, and finally you have the final estimation. We're also going to read it here. So I'm gonna close this window. And that's the result that you can get if you apply our neural network to the SAR image. So I think it looks better on your screen or here, but what you can see is that, so in homogeneous areas, we have no speckle that is left, and we haven't introduced spurious structures. So we haven't introduced artifacts in homogeneous areas. At the same time, we have really well preserved the edges and all the thin structures that are characterizing the image. So it's a good result, the one that we have, and we are going to compare not only from a visual point of view, but also from a quantitative point of view, the result that we got from Merlin with the results that we got with the Lee filter and the simple multi-looking. If there's any question, don't hesitate to raise your hands, and otherwise it will be at the end. So when you train your network in a self-supervised way, you don't have any ground truth information. So the question is, how can I evaluate the performances of my neural network? So the answer is not easy, so I don't actually have a clear answer. The first one is that you need to look at your images. You need to know what you are looking at and what you are interested in. So you need to spend some time to do visual inspection. Then you can also compute some indicators which are limited. So you can compute some set of indicators knowing that each one is going to provide you some information about only one aspect. So you don't have a single proxy that will tell you that your algorithm is better or worse than another one. So that's maybe a limit. It can become a limit, especially if you want to try different network architectures within a given framework to find the best one, because you cannot do it in an automatic way. You need to look at your images. So it can be an interesting research path. Try to understand how you can evaluate the results of your despeckling algorithm. So one simple way to start to have some hints on the quality of your result is to estimate what is called the equivalent number of looks. So what is the equivalent number of looks? We compute it by doing the ratio between the squared mean and the variance. The information that the equivalent number of looks is giving is how many independent samples have been averaged to produce our image. So basically, the higher the equivalent number of look is, the lowest the speckle is, okay? The thing is, this indicator is computed on homogeneous areas, and as you may have noticed, it is 1 divided by the square of the coefficient of variation. So the equivalent number of looks is actually, it favors algorithms that tend to oversmooth an area. So it will not tell you how well you have preserved thin structures in your image. Yet, we are going to compute it. So I have computed here the equivalent number of looks for the original image. Since it's a single look image, I hope to find something which is close to 1, because it's single look, okay? Then for Merlin, the result is provided in amplitude. So we're going to compute this indicator in intensity. So let's do the things in the proper way. I'm going to compute it in an homogeneous area that I have selected. So I'm just going to take this crop. Okay, then I'm going to select the result provided by Merlin. Okay, so that's the yeah, more or less homogeneous areas that I have selected. And here you can see the equivalent number of looks of the original image, which is basically 1, as expected, because it's a single look image. So we see that we have a really high value with Merlin, which means that we have suppressed the speckle from the image, while so it is interesting to see that for the Lie filter in a homogeneous areas, we have used a window whose size was 7 by 7, okay? So we have averaged 49 samples to produce the result on 1 pixel, right? Yet the equivalent number of looks that we have is equal to almost 9, even if we have averaged 49 pixels. Yet the equivalent number of looks should be, it is equivalent to the number of independent samples that have been averaged. So in your opinion, why do we have a value which is less than 49? So the equivalent number of looks should correspond to the number of independent samples that have been averaged. Are my pixels independent
So the
one
more
another?
the more we get away from the center, the more independent. No.
That's not exactly this one the answer. The thing is that when I average pixels within a window, well, in fact, my pixels are not independent. So I won't get a result which is equivalent to the number of pixels that I have averaged, because the pixels are spatially correlated. So I will have a value which is less than what I would have if the speckle was white, meaning that the speckle is not spatially uncorrelated. So it's a way to, well, to see that the speckle is spatially correlated because of, well, some processing that is applied. But with Merlin, as we have trained our network directly on real images, the network has implicitly learned the spatial correlation that is specific to this sensor, so it is robust to the spatial correlation. While if you do some incoherent averaging, you will always have a number of looks which is less than the number of samples that you have averaged, because the samples are not independent. That's the reason. Then the last way to see if we have correctly suppressed the speckle from the images is to rely on the speckle model, which says that the intensity is the product between the reflectivity and the speckle. Since we have estimated the reflectivity, so we have R hat, and we have the original intensity, we implicitly have estimated the speckle component that was affecting our image. So if we do the ratio between the original image in intensity and the restored image, which is the estimation of the reflectivity, you get an estimation of the speckle component. So you can compute some statistics of the speckle component, knowing that your image is a single look image. So you want to find statistics that corresponds to the model that holds for single look data. So you wish to find the mean of the speckle, which is equal to 1, and the variance of the speckle, which is equal to 1. Those are given by the model that you have seen before. So we can try to compute that, and we will see which algorithm is better respecting those statistics in order to evaluate if we have sufficiently reduced the speckle in our images. Okay, so let us have a look at the values that we get, and also we are going to plot. Okay, we are going to plot the residual noise. Oop. Let's see if it's running. Okay, so what we get is, so that's the residual noise of the speckle filter. What you can see is that you see many texture on the residual noise. The reason why you see those textures is because the leaf filter has destroyed all this information that you see in the image. So the reason why you see edges is because they have been destroyed from the original scene. So in fact, what you would like to see when you plot the residual noise is pure speckle. So you want your residual noise to be stationary, in fact. If it is not stationary, it's because you have destroyed some information from the original image. Indeed, that's what we get from Merlin. We cannot see some clear structure on this residual noise. It is closer to a pure speckle, which means that we have not suppressed information from the original image, and we have well preserved the structures of our reflectivity. Another important indicator of the quality of the speckling is the mean value in intensity. So you want the mean of the speckle to be close to 1, because if the mean of the speckle is not close to 1, so the intensity is equal to the reflectivity times the speckle. If the means of the speckle is not equal to 1, you will have a biased estimation of your reflectivity. And you don't want to have a biased estimation of your reflectivity. You want to be as close as possible as the underlying physical scene. So, so we have quite well good results with Merlin, because we are really close to 1 for the mean and really close to 1 for the variance as well. And the last thing that we can do is to plot the histogram and see if it is close to the distribution of the speckle, of the single look speckle in intensity. And what we will see at the end of the computation, which should arrive soon. Tuk, tuk, tuk. It is taking some time. What? Yes. On this part? Yes. Okay. I just wanted to see. Well, it seems stuck. I don't really know why. It is reconnected. Well, it doesn't actually matter. That was the final result. What you should see is that the theoretical distribution fits pretty well with the empirical histogram that is computed on the residual noise provided by Merlin, and it is not actually fitting really well the empirical distribution that is provided by the leaf filter. I think I have lost internet connection, so it's not going to compute the last part, but well, it's not that important. We have maybe a couple of minutes left, so if there's any question either on this part or on the theoretical part that you want to ask to me or to Professor Florence Tupin, well, feel free to ask us questions. Otherwise, you can meet us tonight at the gala dinner and ask us our questions during the dinner.
Any question? No question. Okay, you will have also time to ask your question at the gala dinner, maybe.
And tomorrow
Okay.
as well.
Yeah, of course. I would like to thank Emanuele.